Hello guys, I'm going to repeat what we discussed during our first lecture and then briefly again go over rotational and homogeneous transformations, which we use a lot in robotics. I'll begin by first going over the rotational transformations. So let's say you have two frames. All right, so this is the initial frame x0, y0, z0. And we have a frame that is collocated with this one, right? And here basically we have x1, y1, and then z1. And obviously all these frames are right-hand rule basically. This is your x, your y, and then your z, right? X cross y will actually give you z, and y cross z will give you x, and z cross x will give you y. Okay, so let us say right now that we have a vector that is expressed in frame one, and I'm just gonna draw this kind of randomly. All right, so this is point P, and point P is basically expressed in frame one, and the way you would express that basically is gonna be P1. So P1 is basically that vector P as seen in frame one. So basically here you will have some, x coordinates along this x, and then y, and then z. So P1 basically will have the components x1, y1, z1, right? And because this is a collocated frame, basically we have the same center. P0 is going to be equal to x0, y0, z0. All right, so this is what I have. So now, how can I get the actual relationship, or how can I get the transformations? So given x1, y1, z1, I should be able to calculate x0, y0, z0 based on the rotational transformation that actually exists here. And let us actually begin by doing this. So I'm gonna actually begin by describing or writing what is a vector P1 and frame one. So here I'm gonna write P1, right? Which is equal to x1, I1, where I1 is a unit vector along x1, plus y1, j1, plus z1, k1, where j1 and k1 are also unit vector along the y1 and then the z1 axis. Okay. Now, what I can do is I would like to actually project this vector along I0, right? And you guys know that if you want to project a vector, all you do is basically you multiply, you do the dot product, right? So the component of this guy along x0, right? Let me just do this very quickly. So the component of this vector, so basically if I want to project this vector along x0, I will simply do this, right? So I'm gonna do P1, and then I'm gonna do this guy multiply by I, all right? Where I is initially let's just put it I0 just for reference, okay? Likewise, if you do along the Y0, basically you're gonna do that product with J0, etc., right? So P0, right, is gonna be equal to, so I'm gonna basically take this vector, right? And I'm going to multiply the first row by I0, the second row by J0, and then the third row by K0. And you can, so let us do that actually. So you'll see that basically I can kind of write this like a matrix, right? So X1, Y1, Z1, right, as a matrix operation. And now what I'll do is the first one is going to be multiplied by, so the first one I'm going to end up with, again, so the first one, I'm gonna project it on I0, right? So it's gonna be I1 times I0, right? Second column, J1 times I0. And then the third column is K1 times I0, right? So basically that is simply it, right? So when you do this multiplication, you're gonna end up X1 I1 dot I0 plus Y1 J1 dot I0, and then the third one is Z1 times K0. All right, on the second column, basically, I'm gonna multiply it by J0, right? So it's gonna be again, I1 times J0, J1 times J0, and then K1 times J0. All right, now the third row, I'm gonna end up with what? I1 times K0, then J1 times K0, and then the last one is K1 times J0. All right, so if you actually look more into, this vector right here, right? This guy is what? I1 times J0, J1, I1 times I1 dot I0, I1 dot J0, and then I1 dot K0. This is actually nothing but the projection of vector I1 into, right, into the vector I0. All right, so basically here, right, this entry is basically the projection of unit vector I1 on X along the X0 axis. This is the projection of unit vector I1 along the J0 axis, and then this is the projection of unit vector I1 along the K0 axis. I can basically write that as X1 in frame 0, right? And this guy is Y1 in frame 0, and then this guy is Z1 in frame 0. Okay, and then here I have X1, Y1, Z1. Essentially, this is your rotational transformation R01, and then this guy is P1. So if I have a vector expressed in frame 1, I can convert that vector into frame 0 by simply multiplying it by the rotational transformation R01. And let me actually do a brief example on this one right now while we are doing this. Let's say you have a rotational transformation. Let's say this is my X0, this is my Y0, and then this is my Z0. And let's say frame 1 is actually nothing but this guy rotated by some angle theta. Okay, so this guy is X1, this guy is Y1, and Z1 is also along the same direction as Z0. Okay, so Z0 and Z1 are facing along the same direction. This angle is theta, and this angle is theta. Now, what is the rotational transformation between, basically, I want to know R01. So if I have a vector in frame 1, right, so let's say this is a vector P that has, this is X1, and then it has this Y1, what would be like, this guy? What would be X0, and then what would be Y0? Okay, can you guys now spend a minute, pause the video and then work on this and then watch me do this. Try to work on these examples on yourself. That is how you can really learn as much as you can on this topic. Okay, so recall R01 is actually what we said, X10, right? So unit vector X1, how do you basically express that unit vector in the base frame? And then Y1 0, and then Z1 0. All right. What is the unit vector X1? What is X1 0? So X1 0 basically, what is the X component of vector X1? And here you see, obviously, a unit vector will have a unit length of 1. So what is the X component of vector X1? Is basically simply cosine theta. Right? How about the y-axis or the y component of vector X1 in the Y0 frame? It's going to be sine theta. Right? How about the z component? It will be 0, right? Now let's look at the y10, right? So y10, basically you're looking at this vector. So what is the x component of vector y1? I think it will be minus sine theta, right? So you have minus sine theta. Essentially, you're looking at this component right here. So minus sine theta. How about the y component of it? It would be cosine theta. And then this guy is going to be 0. And then how about z1, 0? So this guy is going to be so 0, 0, 1, right? So it has no component of the x, 0, 1. So there you have it. So this is your rotational transformation. Okay. Now, R1, 0, if you want to do the opposite direction, right? Or if you want to do a transformation between frame 0 to frame 1. So if you have a vector in frame 0 and then you want to get it in frame 1, you will simply multiply it by R01. Right? And in that case, basically, what is that? So that is X0 in frame 1, Y0 in frame 1, and then Z0 in frame 1. And turned out that this is actually nothing but the transpose of this guy. So that will be R01 transpose, and then basically you will transpose this function. And the reason for that is the following, right? So now we have, this is my R01, right? If I do R10, right? Basically, I'm essentially doing that same operation, but here basically you will have basically P0, and then you project this guy along X1. So ultimately you're gonna end up with I1.I0, and then this guy is gonna be J1.I0, and then the third column is gonna be K1.I0. And that is basically nothing but the transpose of this rotational matrix. Okay, maybe as an exercise, you can also try to prove that by doing this operation. Basically, you start here by P0, right? And then you multiply it by I1, right? So basically, you're multiplying across the board by I1. Second one, you want to multiply it by J1. And then the third one, you're going to multiply by K1. But here, you're going to end up with I0, 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 right? Because you're starting with P0. Okay, so this is the actual rotational transformation, and this rotational transformation, like I said, if you have two frames basically which are collocated, and in reality they don't have to be collocated. So sometimes they could actually be two frames, you know, and they are not collocated, but you can still do a rotational transformation. When you do a rotational transformation, basically you assume that they are collocated. Let's actually do an example on non-collocated frames. All right. So if you have, and then this is what we are typically going to be dealing with in our course. And let's actually do an example on that. So let's say you have, again, you have a, you know, a base frame, let's say X0, Y0, and then Z0. And then I have some other frame here, X1, Y1, Z1, and then this guy is O1, and this guy is O. Basically, let's say I have a vector P1. Okay, so this vector P is expressed in frame 1, basically meaning you actually have its X1, Y1, Z1 in a frame. So there are two things that I can do here, right? I can try and find the actual coordinates of this particular point in space. I can try and find it in that frame, right? Or I can simply take that vector, right, translate it here, and then do its rotational transformation. When you actually do, when I actually do this, when I say P0 is equal to R01 multiplied by P1, and then notice the index here, right? So R01 multiplied by P1. So basically, you know, this guy has to be equal to this guy to be able to do a rotational transformation, right? If I'm doing this, basically, what I am doing is basically I'm ignoring this offset between the two frames. I'm taking this vector, right? I'm taking this vector which has X1, Y1, Z1, and I'm basically placing that vector here. And when I do the transformation, basically, I'm simply finding the coordinates of this vector in that frame as if you basically, you take it, you put it here, right? And then you apply this rotational transformation on it, and then you find its corresponding coordinates in that base frame. Okay, now let us look into how do you find its coordinates in that frame, right? In the base frame or in the first frame. So basically, you're going to be looking at this vector, right? So I'm going to be actually finding that P0, right? So this P0 now is actually different than this one. This one basically assumes what? This one assumes, like I said, there's no offset. If you want to take into account that there is an offset, well, first of all, if you want to add two vectors, like, well, first of all, let's say that we can actually, you would probably need to actually have the coordinate of frame. You need to know O1 and frame 0, right? So that is that vector. O1 in frame 0. So P now is O1 in frame 0, right? So you want to know the origin of the second frame in the base frame. So these coordinates has to be given to you in terms of X0, Y0, and then Z0. And now you want to take this vector and you want to convert that into X0, Y0, Z0. So basically these two vectors that you add, they have to be viewed from the same frame in order for you to add them. So you cannot add this vector in the X0, Y0, Z0, and then this vector in frame X1, Y1, Z1, right? It will not make sense. It's like you're adding two vectors from two different frames. Although a vector in reality, in space, a vector is a vector, right? So no matter what frame you view it, it has the same magnitude, right? We're not talking about that. We're simply talking how we are actually viewing that vector. So this vector is Z, but for you to be able to capture it well, or to be able to sum these two vectors correctly, you have to use the same frame for you to sum them. You could either use this frame, or you can use a base frame. In this case, we're using the base frame because we're interested in finding the coordinate of that point in the base frame. So now basically what I actually have to do is I'm actually gonna take that vector, right, and then find its coordinates in that vector. So all I'm basically, it's that one right here, right? So R0 times P1, okay? So this guy, if you actually add O10 to it, it's like you're now finding the coordinate of point P in that frame 0. Okay, now obviously in computation we use matrices, and then for us to be able to actually put this into, for example, MATLAB, we have to kind of work around that. And what we'll do is basically we can now rewrite this whole thing as a 4x1 array, basically. So now, basically, P01, you will simply add 1 to this, right? You convert that into a 4x1, and I can actually now convert, I can incorporate O10 and then R01 into a single transformation, and I can actually call that a homogeneous transformation. So R01, remember, this is 3x3, right? So I want to do 0, 0, 0. So below your rotational transformation, you're going to put 0, 0, 0. And then on the last term, basically, you're going to put O10, and then you basically add 1 to this guy, right? Now you want to multiply this guy by here, by P10, and then you're going to put a 1 at the bottom. So if you actually do this operation, what are you going to end up with? So obviously, the last row, you're going to end up 1 is equal to 1. And above, basically, what you will do is basically, if you do this operation, it's like you're taking this vector, and then you're multiplying by these two, right? So this vector like that, and then you multiply it like that. Okay? So you end up as what? P0 is going to be equal to, so you're going to multiply this guy, right? So this guy by this, R01 multiplied by P1, and then the 1 will actually multiply O10. Okay, so this guy is actually called a homogeneous transformation. So H, we refer to it as H. So H01 is actually equivalent to the rotational transformation is equal to what? Remember, so it's X10, Y10, Z10, right? And then O10, the coordinate of the origin of the second frame with respect to the first frame. And then here you're going to end up 0, 0, 0. And then you actually have to have a 1 at the bottom. And the reason why you have to have a 1 at the bottom is, let's say this guy was 0, right? What actually happens is that, or let's say this guy was 0 first, right? If this guy was 0, right? If I multiply this guy by this, what am I going to end up with? So basically, it's like I'm going to cancel the O10 because now the 0 is going to multiply all the indices of this guy, and this will be 0. And in a homogeneous transformation, if I actually put this guy to be 0, even if I have 1 here, basically, if I do this operation, I'm going to end up with a 0 on this vector. And then if I try to do this operation like, separately later, this vector will actually have a 0 at the bottom. If I multiply it by a homogeneous transformation, it's like I'm doing a rotational transformation, because if that vector has a 0 multiplied by a homogeneous transformation, basically it's like you're doing a rotational transformation. So long story short, if you have a homogeneous transformation and then you want to do a rotational transformation only, all you do is basically on your vector, you just put a 0. If you put a 0, basically, you would be doing simply the rotation. So if I have a vector here, right? If I have these two frames and I have this vector, if I simply want to find the coordinates of this vector into this frame, right? Remember, coordinate of the vector. So no matter where the vector is, basically, you're simply looking at its x0 component, y0 component, z0 component. Basically, I will put a 0 in the fourth row. And if I actually are interested in finding the coordinate of this point, the tip of the vector, where the bottom of the vector is the origin of the second frame, basically, I will basically put 1, right? And then that's pretty much all that you need here, right? So this is called a homogeneous transformation. Okay, now if you want to do the inversion, basically, H10 is never equal to H01. You actually have to do the pseudo inverse of this in MATLAB, for example. You have to actually do the inverse of this 4x4 array, okay, to be able to find H10. But overall, all you do is rotational transformation and then the current of first point with respect to 0. So I'm gonna basically do a very brief example on that we actually covered last time. So this is an example that we had. Okay, so this is a a 3 degrees of freedom robot, right? And this is, so just like what I mentioned last time, is every link on the robot will actually have its own frame. So here you can see that link 1 has its own frame, which is x1, y1. So when you rotate link 1, basically x1 and y1 will rotate with it. Link 2, again, x2, y2 will rotate with link 2. And obviously the ground is a giant link, right? We're not gonna have x0, y0 in it on it. So if we, do, let's quickly now try and then do H01, right? Let's capture the homogeneous transformation of H01 in this example. How would that look like, basically? Can you guys like take a minute now and try and solve it? Okay, so H01, right, is gonna be equal to what? Remember, x10, y10, z10, and then o10, and then you have 0, 0, 0, and then 1. Okay. Okay. What is x10 in this case? x10 is what? x10, basically, you're looking at the coordinate. What is the x component of vector x1, right? It is basically, so it basically, the vector x1 makes a q1 angle with vector x0, right? So it's going to be cosine q1, and the y component is going to be sine q1, and then 0. How about y10? So y10 is that vector. So if you actually look at the actual projection here, so you have x0, y0, this is your vector x1, this is your vector y1, and then this is your angle q, right? So the x component is going to be minus sine q. The y component of it is going to be cosine q, right? Cosine q1, and then 0, and then the z10 basically is what? Is 0, 0, and then 1, because they are basically collocated, right? These two vectors. Now the last thing is we want to know O10, right? O10 is the coordinate or the vector from the origin of the base frame to the origin of the second frame, right? So O10, right? How do you express point 01 in the frame 0? It's going to be L1, right? L1 cosine Q1, and then its sine component is going to be L1 sine Q1, and then the third, the Z component is going to be 0, right? And that's it, right? So your actual homogeneous transformation H01 is going to be equal. I can write this whole thing right now. So cosine Q1, sine Q1, 0, 0, and then second row is going to be minus sine Q1, cosine Q1, 0, 0, and then here I have 0, 0, 1, 0, and then the last one is going to be L1 cosine Q1, L1 sine Q1, 0, and then don't forget the 1 here, right at the bottom. So this component is basically the rotational transformation, and here basically you can see that the rotational, like this component here, right? You can see basically that this rotational transformation right here is basically rotation about basically the Z0 axis. We're gonna actually go over these, right? Like rotation about Z0, rotation about Y0, but overall, no matter how the frames are, basically, you can always capture that rotational transformation. And it would be very important for you guys to really make sense of what is actually happening here, what each point basically, or what each entry in this homogeneous transformation actually means to you, right? So basically, this is the solution here, right? C1, etc., cosine 1, sine 1. So basically, we are shortcutting the cosine into this. You can see basically it's exactly what we actually have. In a similar manner, basically, you can obtain the homogeneous transformation between frame 1 and frame 2, and then again frame 2 and then frame 3. Ultimately, you can actually write this whole homogeneous transformation as H03. Right? So sometimes in our note, we actually use T instead of H. It's the same thing. So it's equal to H01 times H12 times H23, right? So now if I actually have a vector in that frame, right, I can maybe annotate here, and then let me tell you something here. Let's say you actually have a vector, oops. Okay, draw vector. Okay, it's not annotating here. Okay,